Okay, we have a tube that contains a thread of mercury that traps air at the end. Okay, so when we deal with this case, right, we have to be mindful that the atmospheric pressure will act through the opening on the thread of mercury. So in this case, the atmospheric pressure, it will act downwards, and I'll represent atmospheric pressure with P subscript ATM. And for the second scenario, the atmospheric pressure, it will act upwards, and the thread of mercury will exert a downward pressure, and I'll call this P with a subscript M to represent the mercury. So in scenario 1, the pressure of the trapped air is actually pushing up against the pressure of the mercury and the atmospheric pressure. So we can establish a relationship which is pressure of the trapped air is equal to the pressure of the atmosphere plus the pressure of the mercury. And in scenario 2, the pressure of the trapped air is acting downwards, and the mercury pressure is also acting downwards, and they are opposing the atmospheric pressure. So it should look something like this: pressure of the atmosphere plus mercury pressure is equal to the atmospheric pressure. And we know that the trapped air is actually equal to the atmospheric pressure minus of the pressure of the mercury. So comparing the pressure of the trapped air in scenario 1 and 2, we can see that the pressure in scenario 2 decreases. And looking at the relationship between pressure and volume, pressure is inversely proportional to volume. As the pressure decreases, the volume will increase. So the answer should be C. When the pressure of the trapped air is reduced, the volume of the trapped air increases. Okay, question 17. We have a pudding called the Baked Alaska. So it's being placed in the hot oven, and we are being asked, why does the ice cream that is situated at this position remain cold? Okay, we can go through the 4 options. Okay, option A, it says that air is a good conductor of heat. This is wrong, because air is a poor conductor of heat. So option B, air is a poor conductor of heat, and it stops the heat from reaching the ice cream from the oven. This is correct, so B is the answer. Okay, we continue to look at option C and D. The metal dish is a good conductor of heat. Okay, this part is correct, and conducts the heat away from the ice cream. Okay, the second part of this statement is wrong, because the ice cream is colder than the oven. So there is no way heat can be conducted away from the ice cream to the oven. Okay, so option C is wrong. And option D, it says that the metal dish is a good conductor of heat. This statement is already wrong. Okay, we have to understand the working principle of a thermocouple. So basically, when the temperature difference between T1 and T2 increases, the voltage that is recorded by the voltmeter will also increase with it. So we can say that the voltage is directly proportional to the temperature difference between T1 and T2. So in order for the voltage reading to be 0, we have to make sure that the temperature difference is 0 as well. So the answer should be C. The voltmeter will read 0 when T1 is equal to T2. That is when there is no temperature difference. Heat capacity, represented by capital letter C, it refers to the amount of heat required to raise the temperature of an object by 1 degree Celsius. So the formula is Q, which represents the amount of heat energy, divided by the increase in temperature, theta. And specific heat capacity, represented by small letter C, is actually the energy required to raise 1 kg of a material by 1 degree Celsius. So the formula, it looks like this: Q over M, which is a mass, and theta. So the difference between heat capacity and specific heat capacity is such that specific capacity involves the mass, but heat capacity doesn't. So the answer, it should be C. Specific heat capacity involves 1 kg of material, heat capacity does not. The energy required to change liquid water into water vapor at the same temperature is called latent heat of vaporization. So what does this energy do? We have to look at the molecular arrangement in liquid water and in gaseous water. So in its liquid state, the molecules look something like this, close together in a random order. Okay, and in gaseous state, the molecules, they are far apart. So the difference between the liquid state and in gaseous state is that the separation is larger. So the latent heat of vaporization is used to increase the average separation of the water molecules. So the answer should be A.